Okay, so this is the final one of the statistical tests that we're going to look at. Chi-squared. Again, if you want to call it chi-squared, that's entirely fine. We're going to have a look at this again in year 13 when we do inheritance, because it comes in quite nicely into kind of Mendelian genetics and whether or not things have been inherited in the way that you would expect them to. So again, we're going to have a look through the equation, and then what do we do with the value? How do we interpret it? So chi-square looks for a connection in categoric data. So there needs to be a label somewhere. So you can have numbers for one of your variables, but you need categoric data for the other. You need labels. So an example that we use quite a lot is black and white rabbits. You can count how many rabbits are black, how many rabbits are white, but the rabbits are either black or white. Or I'm sure other colours are available. But that would be your categoric data. So a couple of examples here, testing the hypothesis that age and political party that the person votes for are independent, or whether or not a football team's results are affected by the weather, something like that. So just to recap, because one of the things you need to be able to understand is when you would use each of the statistical tests. So Spearman's rank is used when you've got continuous data. You can put both sets of data into size order, and it's looking for an association between them. Okay, so it's looking for a correlation between them. Chi-square is looking for whether things are related. So if one thing has affected another thing, so for example with the inheritance, have they been inherited in the way that you would expect? Were the football team's results affected by the weather? And so you need something that is in labels. And then the t-test compares means. So if you can't get two means or more than two means, you can't use t-test. Right, so this is the equation. Again, we do know what this is. This is the sum of, but it's the sum of everything that comes after it. Now, chi-square, you get observed data. That's what this is. So that's the data you can see you've collected. So if we were breeding rabbits, you'd be able to see how many rabbits are black and how many rabbits are white. You'd be able to count that. That would be our observed data. Okay. The team's football results, the football team's results, they would be our observed data. Okay. But crucially, with chi-square, you have to be able to work out your expected value. So in the terms of black and white rabbits, if we were doing inheritance, if we had done both parents were heterozygous, we would expect a 3-to-1 ratio in the offspring, 3 black rabbits, 1 white rabbit, for example. If you were looking at football teams, you would need to be able to work out the expected result. Okay, so you have to be able to calculate what you would expect to happen. You need to be able to predict an outcome, otherwise you can't use chi-square. So the null hypothesis is always that there is no statistically significant difference. So in this case, there's no difference between what you expect to get and what you do get. Now, in terms of inheritance, if you expect to get a 3-to-1 ratio, you actually want to accept, you actually want to reject the null hypothesis. No, sorry, I've just got that wrong. You would expect to accept the null hypothesis. There is no difference between observed and expected. It has inherited in the way that you want. So if you're breeding rabbits and you want a 3-to-1 ratio and you get a 3-to-1 ratio, then you want to accept the null hypothesis, because the null hypothesis is that there is no difference between what you expect to get and what you do get. Now, if you expect to get a 3-to-1 ratio in your rabbits and you get a 3.5-to-1 ratio, that is a difference. But again, you're going to test how much of a difference. Is that difference just due to chance, just random natural variation that you get in biological systems, natural systems, or is it a significantly different result? Okay, so we use it mostly where we have phenotypes. So we use it mostly for inheritance, as I said. So if you accept the null hypothesis, you're saying that, yeah, they have been inherited in the way that you would expect. Your observed and your expected data is the same. So if you were accepting the null hypothesis for the football teams, yes, the weather, or if your observed and your expected are the same, if you're saying the weather has affected their results, then yeah. Right, now, we would have done this in class. If you happen to have a die at home or a dice at home, you could actually do this activity and you could use your own data. And if you want to send me that data, I'll check whether or not you've calculated your chi-square properly. But what we would have done is we would have had a 10-sided dice, okay? You would have thrown it 20 times and written down what your value was, 1, 2, 3, 5, 9, whatever your value was. And we'd have done it in a little tally chart. So how many times did you roll a 5? How many times did you roll a 2, for example? You would have rolled your dice 20 times, worked out how many times you got each number, and then we would have got the scores from the rest of the class. Now, if you're doing this at home, say, for example, you have a 6-sided dice. If you roll it 20 times, tally how many times you get a 1, how many times you get a 2, how many times you get a 3, etc. If you want to give your family members a go of that dice, then you're just going to get more data and that will be brilliant. So the null hypothesis. The null hypothesis would be that there is no difference between your expected and your observed outcome. Now we can predict the expected outcome for this. So if there are 10 sides to the dice, and that's what we would have used in lessons, we'd have had 0 to 9 on the dice that we have in school. So each roll has a 1 in 10 chance of being selected. So you have a 1 in 10 chance of getting a 1, a 1 in 10 chance of getting a 2, a 1 in 10 chance of getting a 3, every single time you roll it. If it's an 8-sided dice, you have a 1 in 8 chance. Now, if you happen to have any board game at home, it's probably a 6-sided dice, so you have a 1 in 6 chance. Then you times that number by how many times you rolled it. So if you were on your own and you rolled a 1 in 6, a 6-sided dice 20 times, you'd have a 1 in 6 times 20. If you get other members of your family to roll it, you'll have a 1 in 6 times 20, because everybody would be rolling it 20 times, then times the number of people that rolled the dice. So if you have 4 family members, it will be 1 in 6 times 20 times 6. Okay? So this is the tally chart we would have used at school. So we would have filled this in. So let's imagine you roll a dice and in your 20 times of rolling you get 3 1s, you get 2 4s, you get 4 7s, and you get, I don't know, 5 9s, whatever. Work out this tally chart. Okay, now the expected is this. That's how you work out what the expected is. So the expected should be exactly the same. So it's 1 divided by how many sides your dice has, times how many times you rolled it, times by the number of people that rolled it. Okay, and then you should work out the expected. So we're just going to imagine for a second that the expected works out to be 9. Then you should have exactly the same number for every single one. They all have the same chance of coming up. Okay, now you just fill in the rest of the table. So observed minus expected, there's your observed minus your expected. So if we had 3 minus 9, we'd get an observed minus expected of 6. It would be minus 6, but again, it doesn't matter about negative numbers because then you're going to square it to get this value. And you do that for every single one of them going along here. Okay, once you've got this number, you divide this number, so you divide whatever that was by your expected. So whatever that was, you divide it by 9 to get this value. Okay, and then all you do, when you've got all of these, you simply add them all up. Okay, and that will give you your sum of. Okay, so if you have a dice, you can have a go. What I might do is, I do have some dice somewhere. I'll try and find them, and I might put some values for you on the Google Classroom so you can have a go and then we'll work through the solution. I'll publish the solution later and you can check. Okay. Right, so critical values, again, will be given to you. Now, the degrees of freedom is exactly the same. It's n minus 1. We had 10 sides to our dice, so 10 minus 1 gives you 9 degrees of freedom. We're going to work to p equals 0.05, and so we get a critical value of 3.325. So again, if our calculated chi-square value is less than the critical value, we'll accept the null hypothesis. There's no difference between the observed and the expected. The dice are not biased, for example, or if our calculated value is greater than the critical value, we reject the null hypothesis. What we see and what we expect to see are different, and that's how you can tell if a die is biased. And you can buy biased die, and at school we have a pack of non-biased die and a pack of biased die, and you have to work out which one's which. So when we get back to school, we'll have a go at this. So if it hasn't, if you are rejecting the null hypothesis, then what you're saying is you haven't got random chance of getting each side. For some reason, the die is falling more on one side than another. Okay, so that's what we mean by biased. You should have equal chance of getting any one of those sides on your die. Right, so that's exactly the same, accept if it's less than, reject if it's greater than or equal to. Right, so we're going to have a look at an example that I can work through with you. So we're going to have a look at some rabbits. So we're going to breed some rabbits and we're going to count the offspring, and we get 38 black rabbits and 9 white rabbits. So we have a total of 47 rabbits. Now that gives a ratio of 38.9, and like I always say, take that down to 1. So that gives you a ratio of 4.22 to 1. And it is perfectly acceptable to have decimal places. So if you remember, if you do a genetic cross, so let's just quickly do this. Might need a slightly thinner pen. Oops, let's make it green still. If you do this, then that's what you get. That's going to be the white rabbit, and then those 3 are going to be the black rabbits. Okay, so that's what you would expect to get. You would expect to get a 3:1 ratio. Okay, let's just get rid of all of this. So that's what you would expect to get. So is 4.22 to 1 close enough to 3:1? It doesn't look it. 4.22 looks quite a bit bigger. Now obviously it's different, and it doesn't matter that it's a different number. You don't have to get exactly 3:1. You will never get exactly 3:1. Apart from anything else, you're never going to get multiples of 4 if you breed rabbit. Well, you might not get multiples of 4 when you breed rabbits. So we need to work out our expected values. Now if you expect to get a 3:1 ratio, you can work that out. We've got a total of 47 rabbits. So we've got 47 rabbits, and we expect 3/4 of them to be black and 1/4 of them to be white. 3 out of 4 should be black, 1 out of 4 should be white. So you can work that out. Now, if the value is small, then our observed values are close enough. We accept the null hypothesis. It has inherited in the way we would expect it to. If the chi-square value is much larger, then we'll probably be rejecting the null hypothesis. They haven't inherited in the way you would expect. And quite often, if it's on an exam, a year 13 exam, you would be then asked, suggest why it hasn't inherited. And we'll do the whys next year when we do the inheritance topic. Okay, so chi-square measures the size of the difference. So you've got that chi-square value. That chi-square value represents the difference between 3:1 and 4.22 to 1. And then we again need a critical value to compare that to. So this is the equation. Now this should be bigger. This should go like that, but I couldn't find one anywhere. So we've got our observed. We got 38 black rabbits and 9 white rabbits, and we can work out what our expected should be, because 3/4 of them should be black and 1/4 of them should be white. Okay, so let's have a look. So first of all, we need to work out what our expected values should be. Now, sometimes they give you a formula. They ask you to times the row by the column or something like that. But for inheritance, you should know, because we would expect to get a 3-to-1 ratio. Or if you do something called a dihybrid cross next year, you could get a 9-to-3 to 3-to-1 ratio. Either way, you know what your expected values are. So we had a total of 47 rabbits, 38 black, 9 white. Now, if you work out this properly, what you should get is 3/4 or 75% should be black, and 1/4 or 25% should be white. And so that's what you should get. Now, do not round up. Keep these decimals. Okay. Now I have rounded up to 2 decimal places. Keep them as big as you can for as long as you can. Again, you don't want rounding errors. Okay, so these are our expected values. These represent the black ones, these represent the white ones. Okay, so you are usually given a table and you just fill in what's missing. So we had 38 black rabbits and 9 white rabbits. We calculated 3/4 of them should be 35.25, 1/4 of them should be 11.75. And so the first thing you do is you take these two things away. And so you get these numbers. So it is O minus E, observed minus expected. Again, you get a negative number here. Don't worry about it, because then what you're going to do is square the number you had previously to get these numbers. And then what do? You take this number and you divide it by the expected for that set of data. And then this one would be divided by that one. And so when you do that, you get that value for the top row and you get that value for the second row, and then all you do is sum them, sum of everything that comes afterwards, and so you end up with this chi-square value. So that is your final chi-square value. Okay, so what does that mean? Well, the bigger the value, the greater the probability that the observed results differ from what you expect. So you would be saying, no, it hasn't inherited in the way that we would expect. So you need your whole degrees of freedom, and you need to look up your critical value. Now the degrees of freedom is how many groups you've got minus 1. It's still n minus 1. We've got black rabbits and white rabbits. So for us, n equals 2 minus 1. So we have black rabbits and white rabbits, n minus 1 will give you 1 degree of freedom. Okay? So critical values, again, they are usually given to you. Now sometimes for these, for chi-square, you're given 2, and we're going to have a look at an example where you're given 2 as well. So the critical value is what you are going to compare your chi-square value to. So if our value is less than the critical value, we accept. So if it's less than, we accept. If it's greater than or equal to, we reject. Okay? Now, again, we're going to usually use 95% probability. So P equals, that's terrible. Rid of that for a second. So P equals 0.05. But again, if it gives you more than 1, you use more than 1, and we'll have a look. So if our value is greater than the critical value, we reject. There is a statistically significant difference between the observed and the expected, and always relate it back to the question. So there is a significant difference between the number of black rabbits and white rabbits we expect to get. So critical values. So here you can see they have given you 2 critical values. Now we need to use both. If you're given more than 1, use more than 1. Now our value was 0.8 something, I think. We'll have a look in a minute. 0.85 was it? Our value is between these. So we are going to be accepting at one level and rejecting at another level. Now remember, 0.01 is the same as 99%. 0.05 is the same as 95%. So if our value is in the middle, what we're saying is we are between 95 and 99% confident. We are 95% confident. We are not 99% confident. Okay, so let's have a look. So I've just put the critical values up here for you just to remind you. So our value, there you go, I remembered, is 0.85. This is less than the critical value of 1.24 at p equals 0.05. So we accept the null hypothesis. There is no significant difference between the number observed and the number expected in your black and white rabbits. It has followed the expected pattern. However, at p equals 0.01, you can see, oops, trying to underline the right thing, you can see our value of 0.85 is greater than the critical value of 0.57. So we would reject at that level. Now that doesn't mean you reject the whole thing. It means we are between that was supposed to say and. We are between p equals 0.05 and 0.01. We are between 95 and 99% confident. We are greater than 95% confident, but we are not 99% confident. Okay? And that's absolutely fine. You can still say it has followed the inheritance, because 95% for inheritance, when you're doing breeding programs, that's acceptable. But for your exam, you need to compare against both critical values that you're given, and you would accept at one level, reject at another, and you'd get a mark for each of these. So if you only do one, you won't lose all your marks, you will only lose one of them. So if you just did this bit, for example, you'd only get one of the marks, or if you only did this bit, you would get one of the marks. If you do all of that, then you will get both marks. For the conclusion, you get marks for working out the chi-square value, and then there are marks, there's usually 2 marks for the conclusion. This would be the conclusion. Okay? Right, so there are some exam questions in your book, and you can work through those in your own time. And again, put any questions that you've got on the Q&A sheet, the doc on the Google site, on the Google Classroom even, sorry.